All right, folks, I'm going to get started. Welcome back, everyone. Welcome back to the beginning of the 7th week together. Yeah, we're very, very deep into this process. We're just about at the halfway point, which is pretty cool. That means only half more of this to go before a nice long break, which I'm sure all of us will enjoy. But in order for us to enjoy it, we have to work really hard now for, however many more weeks, 7 or 8 weeks left. Fortunately, there is a break coming up. Of course, that can be a mixed bag. It depends on how you approach it. So I hope that you approach it as an opportunity to get caught up in stuff, get ahead in stuff, prepare yourself for that final, 1.5, whatever, 2-month march to the end post the break. So make sure that you do take it as an opportunity to spend the time to do as much as possible to, get on some stable footing and have like a clear roadmap on how you're going to succeed moving towards the end of the semester. Of course, you should also enjoy yourselves because it is a break in name. So take a couple of days to enjoy your lives or whatnot, but don't forget that this is school. You're in the middle of school. Like you're going to get a lot of time once this is all over. So just don't forget like how important this whole thing is that you've taken on, and the fact that even during that week break, like you're still in the middle of it. So we have about a week left after this one before that happens. We're going to cover the rest of production today. We're going to start talking about costs on Thursday and continue through next week. And I think we might jump a little bit further than that next week. I forget exactly. But beyond that, once we get back, there'll be like 1 or 2 weeks before the second exam. So, there's just once we hit that first exam, like it's kind of like the domino effect. Like it's just like one thing after the next. So it's certainly the time to be really in this process. And again, it's really easy to kind of get out of this whole process and lose the momentum that you might have gained going into spring break. So just try not to let that happen. If you want some party momentum, you will get it in the summer. Like this is not the time for it. So I hope you do take advantage of that time and things work out. Are there any questions about anything with respect to this class, how things work? Anything that we've done or will be doing? All right, so we'll finish production today. I'll set up the mini paper for this one today, but any chapters we finish subsequent to that, I'll set up the due dates post the end of spring break at the very end, so that you have that opportunity during spring break to kind of write a couple, knock them out. And remember, you do have that open chapter submission option as well, so if there's a chapter you want to go back and kind of write something about, opportunity exists. So knocking out the paper now is a really good idea, because that once the second round of midterms hit, it's like nonstop basically after that. Papers, finals, like it all kind of rains down on you at once. So you want to knock as much stuff out as possible now, so that you don't get back into that tight corner where you're just like you're spread as thin as possible and you just aren't able to do everything to the best of your capacity. So it's all about demonstrating that optimal capacity that all of you are able to work at all times. And part of doing that, part of being able to do that is time management. How well are you managing your time? How much of a plan do you have for, like something like a semester where that it's like a specific time frame with all sorts of assignments and whatnot that are being sprinkled throughout, that if you don't manage it properly, it can all end in disaster. And we don't want that. We want things to work out. So make them work out. All right. So we are talking about production again. And again, this is all about setting up the framework for being able to analyze like how prices are set in varying market contexts. And the contexts differ with respect to how competitive they are. And we need a framework of costs in order to measure that against the benefits of selling in those markets, which is the revenue that firms can earn. And then that ultimately gets us to those insights about how varying market conditions will yield varying price outcomes. And again, like the life is more complicated than the simplicity, the models that we assume here, but it is meant to be sort of like the most general and most sort of adaptable case. And once you understand how all this works in these like benchmark cases, like you can then compare the more complex cases to what the intuition that you gain from the analysis we do here. So again, to set up the cost, we need to set up the nature of production, which informs costs. And so that's what we've been doing in this chapter. We talked about short-run costs, short-run production, the short run being defined as a time period in which at least one input into production is fixed. We assume that input to be capital. In the long run, that's not the case. All inputs into production are variable, and therefore the firm is free to choose the varying combinations of the inputs that will yield the amount of output they're looking for. And ultimately, they're looking to do that at the least cost possible. So the framework that we start to set up today will get us to that insight. We'll only set up the production side of it today, and then once we get into costs, we'll set up the cost side, and then those will interact to get us to that optimal selection of inputs. In the long run, that minimize costs. And you'll see that the framework is very similar to the rational consumer choice model framework that we covered. So there will be curves that look like indifference curves. There'll be curves that look like budget lines. And so the optimal choice of the inputs that minimize costs for a specific production target will be very similar to that optimal consumption choice as far as like the mechanics of it, the underlying mathematics of it. And so if you did a decent job of kind of learning all that stuff, then a lot of that information will help inform your ability to learn this new application of a very similar framework, but obviously from a completely different perspective on the market, the production side. So that's what this is about. It's about kind of establishing the production side of this long run situation, and then we'll get to the short run costs and then the long run costs, and then it'll all come together. So part of what we'll talk about today is like the effect of long run production on what is called returns to scale, which is like how efficiently are inputs able to produce outputs. So if you have increasing returns to scale, if you increase each of your inputs by some proportion, the output will increase by a greater proportion. If you have constant returns to scale, then that will be equivalent. The proportional increase in inputs will lead to a proportional increase in output. And if you have decreasing returns to scale, then increasing your inputs by a certain proportion will increase output by a proportion less than that. And so a lot of the nature of production can be sort of captured in the production function, and certain production functions will have varying characteristics with regard to returns to scale, which will then inform costs, like I said, and then ultimately have a huge play a huge role in like the competitive nature of the industry that enjoys that type of production and those type of costs. And so this is all linked ultimately to like very profound insights about like what is it that makes one industry less competitive than another industry. And it's a pretty powerful framework, so try to learn it. All right, so previously, again, we started with the basic sort of relationship that underlies all the intuition, which is the production function, the relationship between inputs and outputs. We assume that there's only two inputs in the simple case, and that is capital and labor. Labor being obviously the workers, capital being the catch-all term for anything else used to produce, mainly people-made things like machinery, buildings, etc. So we can relate that relationship via a general specification of what the relation looks like, which is that quantity is a function of both capital and labor. Quantity is, of course, the dependent variable, capital and labor being the independent variables. So again, in the long run, we have the long run and the short run are important as far as like understanding like how all of this works and how and the implications it has for the firm's costs and the nature of the industry resulting from that. So again, the short run is the longest period of time in which at least one of the inputs into production cannot be varied. So regardless of what that input is, as long as there's an input that cannot be varied, then you are by definition in the short run. And once all variables are input, then we are in the long run. So the input that can be varied is the variable input. The input that cannot be varied is the fixed input. So we started talking about production in the short run. In the short run, we represent production as a total product curve. Essentially output as a function of the variable input, which is labor. And the slope of the total product curve represents the marginal product, the extra amount of output that can be produced by employing an additional person at any given level of employment. So here, the marginal product of labor for the second person is 12. That means if we hire an additional person, they will produce 12 units. This curve down here plots the marginal product curve of this very specific production function that has a very specific story behind it that, again, is what generalizes this case to the most general case possible. A production process that initially will begin with just like nobody working, and then a few people will be hired. And as the first few folks are hired, they divide up their tasks, their specialization, there's division of labor. And because of that, the marginal product will be increasing. So that's the range over which there's increasing marginal returns to labor. Each additional person produces more output than the prior person. But because of a short run and the limitation of the capital that the workers have to work with, they will run into a situation in which they just won't have enough capital to go around. Like, you hire more people to produce more output, which is the only way in the short run that output can be increased, because that's the only variable input. But as you hire more and more people, and they start to try to increase their output in the most efficient way possible, they do wind up getting in each other's way, not having enough machinery to go around, etc. So in the short run, due to that limitation, there are diminishing marginal returns to labor after a certain point of production, after a certain scale. And so each additional person produces less than the prior person, but the amount they produce is positive. And so down here again, we have the marginal product curve that does track the slope of the total product curve, which again represents the marginal product of labor. And we see that past this point here, we run into that diminishing marginal returns to labor range, in which again, the marginal product is diminishing. You can say decreasing marginal returns to labor, diminishing marginal returns to labor. And then eventually it can get so bad that hiring additional people will get you into that negative returns range, in which the additional folks actually lower the total amount of output and the marginal product is negative. And then we talked about how we can identify diminishing returns mathematically by checking the second derivative on the production functions. So this linear production function, we checked it, has a constant marginal product for both labor and capital, which means that the second derivative is going to be equal to 0, which means that these production functions don't exhibit diminishing returns. They exhibit constant returns to the labor input. The additional units of the input produce the same amount as the prior units. Like, that never changes. The marginal product never changes. And again, like, the way that we specify the production function will sort of reflect the nature of the production process that we're interested in. So, you might have a production process that has a linear production function associated with it, and so therefore it makes sense to use that kind of production function. But if you're looking to capture the fact that there are diminishing returns, then you need to specify a very specific production function, which can be estimated using regression techniques, statistical techniques to actually calculate this stuff. And so, that's what the whole point of this is to kind of like be able to kind of identify like which production function will exhibit the characteristics that we're interested in. This one we checked the second derivative, and it actually had positive second derivatives, which meant that it exhibited increasing returns to the labor input. And then finally, we looked at this production function here, which we call a Cobb-Douglas production function, which we'll talk about more today. And that one does exhibit the diminishing returns that we were looking for. Again, we figured that out by checking the second derivative. All right, and then we talked about measures of productivity and how they're going to be important as far as like understanding, obviously, how productive a production process is, but ultimately establishing a pattern that will provide like intuition into like the nature of like the patterns of costs that the firms will face or face in general based on these general characteristics. So one measure, of course, is the marginal product. That tells you the extra amount of output produced by employing an additional person. Another measure is the average product. So at any given level of your labor input, like on average, how much is everybody producing? Just graphically, you can draw a ray from the origin, just a line from the origin, and wherever it hits on the production function at that point, if you take the slope of that ray, it will give you the average product. So at this point here, it hits the production function at the combination of 2 workers and 14 units of output, which in this case was meals. We were looking at meals. 14 divided by 2 is 7. So the average product of labor for 2 employees is equal to 7. And we see that the slope of the production function is steeper than the slope of the ray, and therefore the marginal product is greater than the average product. Average product is going to be changing as additional people are hired. If the additional amount of output they can produce is greater than the average product, then which essentially means that the marginal product is greater than the average product, then it's going to bring the average up, right? On average, everybody's producing 2, and then you hire someone whose marginal product is 3, so that's going to bring the average product up. Over a certain range, the average product is going to be pulled up as a result of the marginal product being above it, and that happens over the range of increasing returns and also decreasing returns, as long as the marginal product is still over the average product. And we see that relationship plotted down here with the marginal product curve and the average product curve. So the marginal product, again, will increase up until the point where the firm hits that short run wall and exhibits decreasing or diminishing returns, which then starts to pull down marginal product. But average product will be brought up even past that point, and then at the point where they are equivalent, that's where the change happens, and marginal product dips below average product, and average product starts to then be pulled down as well. It happens at the point where the ray from the origin is exactly tangent to the production function, and beyond that point, we see that the slope of the rays is going to be, in this case, it's going to be greater than the slope of the production function, which again means that the average products are going to be greater than the marginal product. Marginal product will be bringing down average product. What's important is just to understand this relationship here, and graphically, it's just, if you understand it graphically, it's just meant to kind of give you more intuition into it. We also talked about the practical significance of the average marginal distinction via a couple of examples where we established that the optimal allocation of a productive input across production processes is going to happen at the point where the marginal products are equivalent, as opposed to equilibrating the average products. Doing that will actually wind up in a less efficient allocation of the productive resource. In this case, we were talking about boats going to different parts of the lake to fish, and we looked at marginal products, and we saw that it made sense to keep increasing the amount of boats on the west end until its marginal product was at least greater than or equal to the marginal product of the boats on the east end, which is constant. So we figured out that 2 boats should be sent to the west end, and then 2 boats should be sent to the east end, because post the second boat, the third boat yields 90 extra fish. The marginal product of that third boat was 90 fish, which is less than the marginal product of the third boat on the east end. All right, now let us jump into the long run. So the short run production function has capital fixed, right? So we fix capital at some value k naught. And we were able to describe the production function as a simple 2-dimensional diagram, because again, when it's the short run, then production is just a function of labor. So therefore you have output as a function of one variable, labor. With both capital and labor variable, we require 3 dimensions. Just like when we did the utility function and looked at utility as a function of just one variable. So we had that example where that girl was eating clams, and the utility function was just like a concave utility function that was like that had diminishing returns as far as like the additional utility from additional clams, and that was a simple relation to represent because it was just utility as a function of clams, just a 2-dimensional relationship. But when we established that utility was a function of 2 goods, basically adding a 3rd dimension and therefore needing to analyze a 3-dimensional relationship, that created, you know, some complexity that couldn't easily be represented by 2-dimensional graphs. But then we did establish that by chopping up that utility function and then looking at the traces of the edges of the utility function, that which were known as indifference curves, that was a means of sort of analyzing the more complicated situation in a 2-dimensional setting. And so we're going to do something similar here, where quantity is a function of capital and labor, so you're going to get a 3-dimensional relationship. But we're going to do something similar as far as like chopping it up and having the edges represent basically combinations of outputs that yield a certain level of input. Varying combinations of the inputs that yield a certain level of output at each level of the production function. All right, so consider like a production function that looks like this. It's a very simple case in this case where quantity is a function of capital and labor, and this is a specified form. They're being multiplied by each other and then multiplied by some constant 2. Suppose we want to describe all possible combinations of capital and labor that give rise to a particular level of output. Let's say quantity of output is 16. So we set Q equal to 16, divide both sides by 2, and then we'll solve for capital in terms of labor. So we'll assume capital is on the y-axis and labor is on the x-axis all the time. So I'll just switch these 2, and then I divide both sides by L, and I get capital equals 8 over L. So what I've just solved for is an isoquant. Iso means same, quant, quantity, so same quantity. It's a set of all input combinations that yield a given level of output. So we were looking at an isoquant that yields, that corresponds to the level of output, which is 16 units. Graphically, it's this isoquant here. It's got a similar shape to the indifference curves. Again, in this case, we're looking at capital as one input into production, labor as the other input into production, and the combinations of the 2 that will yield that same level of output 16. So if, let's say, this firm is using 12 units of capital and roughly 1 unit of labor, they're able to produce 16 units of output. If they use 1 unit of capital and 8 units of labor, they can still produce 16 units of output. This is a more labor-intensive production process. A represents a more capital-intensive production process, meaning more capital relative to labor is being used. Labor-intensive, more labor relative to capital is being used. As we go further out from the origin, we can have isoquants representing higher levels of output, just like we could have indifference curves representing higher levels of utility. Again, back in that in that framework, each indifference curve represented consumption bundles that yielded the same level of satisfaction to the consumer that we were modeling the behavior of. Now we're modeling the behavior of a firm, and each combination of inputs along an isoquant will yield the same level of output, mechanically in the same way that the indifference curves worked with respect to the utility and the consumption bundles. There are isoquants everywhere. So even if we don't see them, they're there, representing each level of output. So this point C is going to represent some level of output on an isoquant between 32 and 26, and D is going to represent some level of output for an isoquant at some level between 64 and 32. All these isoquants mapped out are called an isoquant map. So again, how they relate to the actual production function is that they are traces of the edges of a three-dimensional shape. So there's also a geometric technique for deriving the isoquant map, one that is similar to the derivation of the indifference curve map. So here is capital and labor. So this is the y and x axis, and it's just representing the plane over which on which the isoquants exist. And what they are is just traces of the outside of this production function, which is three-dimensional. There's a third axis, the z-axis, which represents quantity. So it's like the height of this like weird kind of hat-shaped production function. So it would be something like this. And then the height represents quantity. And again, if you slice the production function at some level, it's going to represent a level of output. And therefore, all the combinations of the labor and capital along that edge will represent combinations of the outputs, of the inputs that will yield the same level of output, again, corresponding to the height of the three-dimensional production function. But you know, we trace them, and then we like kind of smash them down, and then place those traces along that XY plane that we're also familiar with. And so it becomes a more manageable way of understanding the production function without having to understand like multivariable calculus. So again, so here's the end result once again. These are the traces of this three-dimensional shape. And so if you think about this, then you can understand this better, because you understand that as we're going further out, we're actually dealing with edges of a structure that are higher up than the prior edges, corresponding to higher levels of output. All right, so there is a slope to each of these curves, just like there was a slope to the indifference curves, which was the marginal rate of substitution, the rate at which a consumer would trade off one good for another in order to maintain their overall level of satisfaction, their utility. The concept here is very similar. It's the analog of it, but we call it the marginal rate of technical substitution. It's the rate at which one input can be exchanged for another without altering the total level of output. So at any given point, there's going to be some exchange that you can make between labor and capital in order to maintain your level of output the same. A simple but important relationship exists between the marginal rate of technical substitution at any point and the marginal product of the respective inputs at that point. So in a small neighborhood of, let's say, this point A, suppose we reduce capital by some amount, we'll call it change in K, and augment labor by some amount, the change in L, just sufficient enough to maintain the level of output. If we let the marginal product of capital at A be denoted by MPKA, and the reduction in output caused by the loss of K to be change K, then the reduction in output caused by the loss of K is going to be equal to the product of these two. So as we're moving down and we're using less capital, we're losing some productive capacity, reflecting what that amount of capital can yield. And so that's going to be equal to the change in capital times the marginal product of capital at that point. If we let MP subscript LA denote the marginal product of labor at point A, then an increase in output caused by an increase in labor by some quantity change in L is going to be equal to, again, that amount of output, that amount of labor times the marginal product of labor at that point. Since the reduction in output from having less K is exactly offset by the gain in output from having more L, because we have to maintain the same level of output along each isoquant, then these two expressions will be equivalent, much like was the case when we were looking at the indifference curves and the marginal rate of substitution, and we were examining what happens as far as overall utility when we're moving along the indifference curve. Well, if you're consuming less of one good, you're losing some marginal utility for that good, but you're consuming more of the other good, and you're gaining some marginal utility from that other good. And so they were equal, which allowed us to derive an expression for the marginal rate of substitution as a ratio of the marginal utility of the good on the x-axis to the marginal utility of the good on the y-axis. Here we can derive a similar expression for the slope of the isoquant, the marginal rate of technical substitution, via this method here. So again, we'll derive the standard sort of slope expression, the change in K over change in L, by dividing both sides by the change in L. And then we want to isolate that, so we want to divide both sides by the marginal product of capital. So I did that there. I divide both sides by the change in L, and then I divide both sides by the marginal product of capital. These cancel out. These cancel out. And so we're left with this expression for the slope of the isoquant, which is going to be equal to the ratio of the marginal product of the input on the x-axis to the marginal product of the input on the y-axis, which again, we assume to be capital, and on the x-axis, we always assume to be labor. And so therefore, the marginal rate of technical substitution can be expressed as the ratio of the marginal product of capital to the marginal product of labor. So underneath it all, beyond just like what it means, mathematically, it's exactly the same thing as what we did in the rational consumer choice model. In consumer theory, the shape of the indifference curve tells us how the consumer is willing to substitute one good for another. So we were able to look at different indifference curves and say that those represented preferences of different types of consumers. In production theory, we have an essentially similar story, and it's told by the shape of the isoquant. These are the extreme possible sort of cases for the isoquants, and it reflects how perfectly substitutable the inputs are into production. If they're really easily substitutable to the extent that they're perfect substitutes, and therefore you can just keep substituting one input for the other, and the rate at which you would exchange them would not be affected by the nature of the production process. Then you have the perfect substitutes case, which can be represented by linear isoquants. So this one represents a production process in which cars and gasoline are combined to produce trips. So there's different types of gasoline that can be used to produce a certain amount of trips. This represents producing one trip, producing two trips, producing three trips. And the marginal rate of technical substitution is equivalent, meaning that you could wind up just using Amoco or just using Texaco to produce, the one trip, and it would be possible to do that. So again, we can substitute 1 gallon of Amoco for 1 gallon of Texaco and still produce the same number of trips as before. So the marginal rate of technical substitution between Texaco and Amoco remains constant at 1 as we move downward along any isoquant. But that's not the case for the convex isoquants that we were looking at and will be looking at, representing the most common case. These are the extreme possible cases. This is the other extreme possible case in which the inputs into production are not substitutes, but they are complements. And the only way that you can increase production is to increase both of them in the same proportion. It's called the Leontief production function. So this one describes a production process for typing letters using two inputs of typewriters and typists. So let's say you have only one typist. Well, you can use a bunch. You can employ a bunch more typewriters, But that's not going to yield any more output because you need to increase both typists and typewriters in order to increase the amount of output, which is like, documents. So the two are perfect complements. They can only be increased in fixed proportions. Inputs are most effectively combined in fixed proportions, and therefore there is no marginal rate of technical substitution for this case. There's no rate at which you can substitute one input for another. The inputs are perfect complements. They have to be increased in fixed proportions. We could represent these relationships algebraically, of course. In that first case where the inputs were perfect substitutes, that is a case in which we have a linear production function, like the one that we saw in the diminishing returns to labor mathematical example, where the marginal products were constant, and so there were constant returns to the productive input. So we can represent it by this type of expression where capital and labor are being added together, and each one has some coefficient on it which represents their productivity. If you just take the derivative with respect to capital, you'll get the marginal product of capital, and it's just going to be A. You take the derivative with respect to labor, you'll get B. That's the marginal product of labor. With a linear production function, again, inputs are perfect substitutes. There's a perfect linear relation between all inputs and total output. Suppose it takes it takes workers at a plant 4 hours to produce as much as 1 unit of capital, or one machine can make in 1 hour. That means machines are going to be 4 times as productive as labor. In this case, the production function is linear, with A being 4 and B being equal to 1. So that's what this production function is telling us. The inputs are perfectly substitutable, and capital is 4 times as productive as labor. In the case of the complements, the inputs into production being complements, that's represented by what's called a Leontief production function, and it's given by this expression here. That's basically telling us that the amount of output that can be produced is going to be the minimum of either of these terms. Whichever of these terms is lower is going to represent the amount of output that can be produced. A and B are constants. So the Leontief production function, also called the fixed proportions production function, implies that inputs are used in fixed proportions, like the typewriter typist case. So again, this is the linear production function case, and it will have linear isoquants, whereas the Leontief production function represents the perfect complements case for inputs, and it's going to have right angle isoquants. Quick practice problem, Leontief production. The engineers at Morris Industries obtained the following estimate of the firm's production function. It's a Leontief production function. How much output is produced when 2 units of labor and 5 units of capital are employed? So based on, it's going to be A, right? It's going to be the minimum of the two. It's going to be the minimum of the two. So in this case, using 2 units of labor is going to equal 8 units of output. And so using 5 units of capital would yield 15 units of output, but we can only produce 8 units of output because they need to be increased in fixed proportions. So if this was equal to 1 unit, then that would dictate the amount of output that could be produced, which would be only 3 units. So you need to increase them both in some proportion in order to that will not change based on the needs of the production process. The point is, like everything else, like with the math, it's like you have to understand, like the math can capture a lot of information and provide a lot of information. So if like an analyst is being brought in to provide insight into like a business, and they need to estimate a production function for it in order to be able to estimate costs, etc. They will look at the production process and they'll say, well, this looks more like a perfect complements case, so we'll need a Leontief production function, and depending on the needs of the firm, like the coefficients will dictate what that production function will look like. All right, so again, since the minimum of the numbers 50 and 8 is 8, we know that 5 units of capital and 2 units of labor produce 8 units of output. All right, now for the most common case, which is the Cobb-Douglas production function, which is the one we'll use. In this case, the inputs will not be perfect substitutes; they will be imperfect substitutes, meaning that as you increase either one input or another, the rate at which you can switch them will change. So the most commonly used production function in economic analysis is the Cobb-Douglas production function. It has this form here, where you have capital and labor being multiplied, each one being raised to some exponent, in this case represented generally by alpha and beta, and the whole expression being multiplied by some constant m, which can be equal to 1, in which case you wouldn't see it, but it'll always be there. So the exponents will be between 0 and 1, and m, this coefficient, can be any positive number. To generate an equation for the Q naught, so some level of output corresponding to the isoquant we're interested in, we fix Q at that level like we did earlier with the production function we looked at, and then solve for K in terms of L. So for the particular Cobb-Douglas production function that we see here, capital raised to the 1/2 power, labor raised to the 1/2 power. The Q naught isoquant will be, so again, you want to solve for capital in terms of labor, so divide both sides by L to the 1/2. And now we want to isolate K, so we're going to raise both sides to what power here? To isolate K. 2, right? We're going to square both sides, the reciprocal of the exponent on the variable we're looking to solve for. And so therefore this equation here will give us the equation for the isoquants. And then depending on what level of output we're looking at, the equation will look slightly differently corresponding to each different isoquant as we move further away from the origin. So if capital equals 2 and labor equals 2, so we plug those in there, then our output is going to be equal to 2 units, which again is going to correspond to this isoquant. All right, practice problem 8.5, Cobb-Douglas marginal and average products. A firm can manufacture a product according to the production function K raised to the 3/4 power, L raised to the 1/4 power. Calculate the average product of labor when the level of capital is fixed at 81 units and the firm uses 16 units of labor. All right, so there's a couple of ways it can be done. So remember, average product is equal to quantity divided by the amount of labor. So you would need the quantity amount. So one thing you could do is just plug in capital and labor, find out how much output that would correspond to. You'll get a Q, and then you'll divide that by the number L, and that'll give you the average product of labor. And the other thing you could do is you could solve for the average product of labor algebraically, and then just plug in your numbers once you have that expression for a general average product of labor based on this production function. So the first thing I did was I fixed our capital at 81 units, putting us into the short run. So this is my short run production function. And again, average product of labor is Q divided by L. So I divided this expression by L. So you've got L raised to the 1/4 power divided by L. That's going to equal L raised to what power? Negative 0.75, right? That's what we're going to get from this, or negative 3/4. So that's my average product of labor general expression. And now just plugging in 16 units of labor in there will get me to the average product of labor, which is 3.375. And that means that with 16 units of labor, on average, each laborer is producing 3.375 units of output. But remember, you have to specify that it's happening at that level because we know that average product is changing as we're moving along the production process, right? Calculate the average product of labor when the firm uses 256 units of labor and interpret it. So we'll plug in 256 units of labor there, whereas before we're using 16 units. Plugging that in is going to get us 2.42. So in this case, the average product of labor has gone down. So we have to therefore necessarily be over the diminishing returns range, right? Because marginal product has to be driving it down, or else average product would be would be increasing. So each of the 256 laborers produces an average of 0.42 units of output is how we can interpret that. Find an expression for the marginal product of labor when the amount of capital is fixed at 81 units. So I'm going to fix my capital at 81 units, get me into the short run. How am I going to get my marginal product of labor? Take the derivative, right? The derivative will get me the marginal product expression. So again, we're going to multiply this whole thing by a quarter, subtract 1 from the exponent on L, which is going to get me to 6.75 L raised to the negative 0.75 power. So now we're going to look at the marginal product by plugging in 81 units. Did I skip that? No, I did. Oh, wait, no. Oh, we're looking for that. That was just an expression, so I got the expression. This is the expression for the marginal product of labor. Illustrate that the marginal product of labor depends on the amount of labor hired by calculating the marginal product of labor for 16 and 81 units of labor. Interpret it. All right, so I'm going to plug in 16 units of labor to figure out my marginal product of labor at that level. So that's going to get me to 0.844. So can somebody interpret that for me? Yeah. I appreciate that. So this is the marginal product of labor at 16 folks. So that means what? I have 16 people. If I hire one more, it won't cost me. That 17th person, right, will produce an additional 0.844 units of output. I have 16 people, hiring one more, that will be their marginal product of labor. All right, plugging in 81 folks, that's going to get me to a marginal product of 0.25. So that means we have what here? We have what kind of returns? Diminishing returns, right? If we see the marginal product of labor is decreasing, so we are in that short run situation that's causing us to diminish the amount of output as we hire more folks. Yeah, so that's the interpretation for that one. I just threw that in. I didn't put the right order on the animation, sorry. Anyway, hiring an 82nd worker would yield 0.25 additional units of output. That's how we interpret that one. So given the change in marginal product, are there increasing, decreasing, or negative returns to the labor input? You already answered it. But say it again. There's decreasing, right? Decreasing returns, we hired more folks, and each additional person is producing less output than the prior person. All right, so now let's talk about returns to scale. And it's important to understand the difference between the returns to the labor input versus returns to scale. So a question of central importance for the organization of industry is whether production takes place most efficiently at large scale rather than small scale. So the term that we use to sort of describe how that's working is returns to scale, the technical property of the production function used to describe the relation between scale and efficiency. The term tells us what happens to output when all inputs are increased by exactly the same proportion. Returns to scale is a long-run concept because it refers to a situation in which all inputs are variable. All right, so the first case is that of increasing returns to scale. It's the property of a production process whereby a proportional increase to every input yields a more than proportional increase in output. So if we double all inputs in a production function with increasing returns, then output will more than double. Such production functions generally give rise to conditions in which a small number of firms supply most of the relevant market. If there are increasing returns to scale, that means that it makes sense for there to be larger firms in the market. Firms that get bigger will have that benefit. They will be able to get more output by increasing their inputs. And so that is one of the important properties of a production process that will dictate how competitive a market can be. If you have a lot of large firms, then you have to be large in order to compete in that market. Being large is what's called a barrier to entry. So that's going to cause other firms to not be able to enter the market easily. Of course, the production process might have constant returns to scale, the property of a production process whereby a proportional increase in every input yields an equal proportional increase in output. So doubling all inputs will exactly double output. In industries in which production takes place under constant returns to scale, large size is not important. Firms can be small, large, it doesn't matter. Everybody experiences the same benefits from either increasing their scale or not. And then you might have a production process that has decreasing returns to scale, the property of a production process whereby a proportional increase in every input yields a less than proportional increase in output. Doubling all inputs results in less than doubling of output. We do not expect to see large firms in an industry in which production takes place with decreasing returns to scale because it costs more to produce if you have decreasing returns to scale. So you want to be smaller versus larger. And therefore, a lot of small firms tend to dominate an industry that has decreasing returns to scale, which means that there is more competition in industries that exhibit those kinds of attributes. All right, how can we identify returns to scale on an isoquant map? So a simple relationship exists between a production function's return to scale and the spacing of its isoquants. As we move outward along this isoquant map, along this ray R, each input grows by exactly the same proportion. So here we're at A. There's 1 labor and 3 capital. At B, we've doubled both. So we have 2 units of labor and 6 units of capital. At C, we've tripled them, and so on and so forth. So again, the inputs are increasing in the same proportion. So we see that when capital and labor are doubled, that output triples. So what does that mean for this part of the production process here? Going from A to B, we have what kind of returns to scale? Increasing returns to scale, right? Double each input, output more than doubles. We have increasing returns. So we see that up until the third one, we're gonna have that property. Beyond that, the firm is going to start exhibiting constant returns to scale. And then beyond that, the firm is going to start exhibiting decreasing returns to scale. So a lot of firms will operate in these type of environments where the returns to scale will vary based on their scale. And a lot of times, there will be a limitation to how firms can get as far as their size. They can get too big, and it's possible for that to actually become a hindrance to their operation because, again, imagine some very simple situation where like 2 huge global companies like BP and Exxon, let's say, merge, then they obviously are going to form a huge gas company, but you're also going to get like a lot of very similar departments, a lot of very similar powerful figures at each firm that are going to have large egos. The departments aren't going to be able to work well together. The egos of those working at the top will generally stop them from being able to have that kind of synergy that you need to be efficient at any level. And so as firms get bigger, these kind of situations will cause them to lose increased efficiency, getting them into the range of decreasing returns, which is what we see here. So again, that's a very general sort of production process. And again, we're talking about the most general cases here. All right. All right, now let's look at how we can identify returns to scale mathematically. So mathematically, to increase all inputs in the same proportions simply means to multiply all inputs by some number C greater than 1. So consider the production function 2KL. If we multiply each input by C there, so you're going to have C multiplying K, C multiplying L. and then we factor out the c there. So we're going to have c squared times 2kl. 2kl is our original production function. So we see that increasing capital by some proportion c and labor by some proportion c will increase output by the square of that proportion, c squared. So we have what, therefore, in terms of returns to scale? Increasing returns to scale, right? Again, this could be two double capital, double labor, and therefore you quadruple output, is what that's telling us there. So output grows more than in proportion to input growth, so this production has increasing returns to scale. If we double the amount of capital and labor, output would quadruple. So I did have the example with 2. So I just factored out 2 there, and then 4 times 2 is 8. So we see that our output is now 4 times what it was before because we doubled our inputs. So drawing on these observations, the definitions of our 3 cases may be summarized as follow. For increasing returns to scale, if you increase each input by some proportion c, then the output will be greater than multiplying the whole output by c. So the proportion by which output will be increased will be greater than the proportion by which the inputs were increased. Is what that's telling us there. Constant returns to scale. Again, you increase each input by c, and that will be equivalent to increasing output by c. And decreasing returns to scale, increase each input by c, and that's going to lead to some output that's going to be less than the proportional output. So it'll be less than proportionally effective. Let's do some mathematical examples. So here's this production function, which is essentially a Cobb-Douglas. You have k raised to the 1/2 power and L raised to the 1/2 power. The question is, does it have increasing, constant, or decreasing returns to scale? So remember, keep track of what we're doing here. We're looking at returns to scale, not whether there's diminishing returns to our labor input. And that entailed us checking the second derivative. So just keep those separate. All right, so there's a couple of ways to approach this. The most straightforward way is just to multiply each input by some factor c and then see if output is increased by more than c. So doing that here, we're going to have c multiplying k, c multiplying l, but it has to happen within the parentheses because, again, k is being raised to the 1/2 power, but k is being multiplied by c and then being raised to the 1/2 power. So if we factor out c to the 1/2 from each of these, we're left with c to the 1/2 times k to the 1/2 times L to the 1/2 times c to the 1/2. So I didn't factor it out of there. I just took them out of the parentheses from the properties of exponents, things that we covered a couple of weeks ago. But now we do have that same common term there. So we have c to the 1/2 times c to the 1/2 is going to equal c to the 1st power. So we see that increasing each of our inputs by c will lead to us increasing our output by c as well. And therefore, we have constant returns to scale. Similar Cobb-Douglas production function. Again, we're going to check it the same way. We're going to multiply each of our inputs by c. We're going to take c out, c raised to the 1/3 power out of both terms. And then you've got c raised to the 1/3 power times c raised to the 1/3 power, which is equal to c raised to the what? 2/3 power. So you've got c raised to the 2/3 power multiplying our original production function. So what do we have here? Decreasing returns to scale. We've increased each of our inputs by some factor c, and our output has increased by less than that, c raised to the 2/3 power. So we have decreasing returns to scale there. For a Cobb-Douglas production function that we've been looking at and will be the common production function that we're going to look at, it's really easy to identify returns to scale by just adding the exponents on the productive inputs. So if the productive inputs exponents are greater than 1, then the Cobb-Douglas production function will exhibit increasing returns to scale. If they're equal to 1, then the production process exhibits constant returns to scale. And if they're less than 1, then the Cobb-Douglas production function represents a production process that has decreasing returns to scale. But you can only do that with a Cobb-Douglas production function. All right, so again, going back to the ones that we already did. So again, here, if we just add them together, we see that they're equal to 1, so we have constant returns to scale there. With the second one, add them together, that's 2/3, so we see that we have decreasing returns to scale, just adding their exponents. And again, just to highlight, again, this distinction between diminishing returns to a labor input versus returns to scale. They are not related. Decreasing returns to scale refers to what happens when all inputs are varied by a given proportion. The law of diminishing returns refers to the case in which one input varies with all others held fixed. So just make sure you keep that separate so that you don't screw up. All right, and let's just do one more practice problem. We'll call it a day. Do the following production functions have increasing, decreasing, or constant returns to scale? What about this one here? Constant returns to scale. It is a Cobb-Douglas production function. We have capital and labor being multiplied, each being raised to some exponent, which is between 0 and 1, and the whole thing is being multiplied by some constant. 4, it's a Cobb-Douglas. We add the exponents, they're equal to 1, and so therefore we have constant returns to scale for this production process. This is not a Cobb-Douglas production function. So let's use our other method for this one. Again, we're going to multiply K by C and then L by C. And then we need to take those terms out of the parentheses. So we're going to have C squared here and then C squared there. And then we're going to factor out C squared. And now we're back to our original production function being multiplied by C squared. So what kind of returns to scale do we have here? Increasing returns to scale. The production has been increased in greater proportion than the proportion that our inputs were increased in. What about this one? We have increasing returns to scale. This is a Cobb-Douglas production function. So just adding the exponents there equals 1.1. So we have increasing returns to scale. If we double each of our production inputs, that means our output will more than double. All right, folks, we're done for the day. Good job. We're done with this chapter too, so I'll open up the homework for it and the mini paper. And that's it. Hope you guys have a good couple of days. I'll see you on Thursday.